The heart of this machine is the multi-material extrusion system. Think of it like a CMYK printer, but instead of colors, it uses functional properties as its ink. The four tools work in a synchronized dance, switching between materials in milliseconds to ensure that the conductive veins are perfectly insulated from the structural bones. This level of coordination requires a custom software stack that can translate 3D electromagnetic simulations directly into toolpaths for the printer. The conductive layer is the most critical. MIT uses a specialized filament packed with high-purity copper particles suspended in a polymer that evaporates during the printing process. This leaves behind a nearly solid copper path. It's the electrical nervous system of the motor, capable of carrying the high currents needed to generate significant force. By controlling the density of these particles, the printer can even create resistors and sensors directly within the motor structure, allowing it to monitor its own performance. Next is the magnetic core. Instead of using solid iron, the printer extrudes a ferromagnetic filament. This material is filled with tiny flakes of iron and neodymium. These flakes are what allow the motor to interact with the magnetic fields produced by the copper coils. Without them, the motor would have no grip on the air around it. The genius part is that the printer can vary the orientation of these flakes as it prints, optimizing the magnetic path for maximum efficiency. The structural material is the skeleton that holds everything together. It has to be incredibly rigid to prevent the motor from deforming under the intense magnetic forces it generates. MIT uses a carbon fiber reinforced polymer for this layer. It provides the strength of aluminum but with the light weight of plastic, making it ideal for mobile robotics. Finally, an insulating layer is deposited between the copper and the magnet. This prevents short circuits and ensures the electricity flows exactly where it's supposed to. The most difficult part of this multi-material dance is the interface between layers. If the materials don't bond perfectly, the motor will fly apart the moment you turn it on. The MIT team solved this by using a gradient transition technique. The printer slightly mixes the materials at the boundary, creating a chemical bridge that is stronger than the materials themselves. This allows the motor to act as a single cohesive unit. It's a level of material integration that is simply impossible with traditional manufacturing methods. Even after the print finishes, the motor is technically dead. The magnetic material is there, but its internal domains are pointing in every direction, canceling each other out. To activate it, the motor undergoes a final magnetization step. This is the spark of life that transforms a plastic and metal block into a functional machine. A massive pulse of electricity, thousands of amps, is sent through an external coil, creating a magnetic field so strong it forces every atom in the motor to align. This pulse only lasts for a fraction of a second, but it permanently changes the material. The iron and neodymium flakes are now locked in place, creating a powerful permanent magnet. The physics here is fascinating. By controlling the shape of the external field, MIT can program the magnetic properties of the motor after it has already been printed. This means you could print 10 identical motors and then program each one to have different torque or speed characteristics just by changing the activation pulse. Because there are no fasteners or separate parts, these motors have zero internal friction from assembly misalignments. They are perfectly balanced because they were grown, not built. In a traditional motor, even a fraction of a millimeter of misalignment can lead to vibration and wear. In a printed motor, the geometry is mathematically perfect, defined by the printer's resolution. This leads to a massive increase in lifespan and reliability. There are simply fewer things that can go wrong when your machine is a single solid piece of hardware. The implications for robotics are staggering. We are moving toward a world where a robot can literally print its own replacement parts, or even a smaller version of itself. In space exploration or remote colonies, this technology is a game changer. You don't need to ship a warehouse of spare motors, you just ship the raw filaments and print what you need. This shifts the focus from logistics to design. If you can print a motor anywhere, the only limit is your ability to imagine new ways for machines to move. MIT's breakthrough isn't just about making motors, it's about the birth of active matter, objects that aren't just shapes but have function and motion baked into their very atoms. Next time you see a machine humming away, remember that we are entering an era where the line between part and process is disappearing. The assembly line served us well for a century, but the future belongs to the machines that can simply wake up and start moving. The engineering behind this is quite literally moving us forward.